We were discussing the BJT device, and we said that, again, it's basically two diodes. So nothing, I mean, the diode physics and the equation for current is very similar to what we've seen before. And what do? We have a junction here between this N material and this P material, another junction here. This is called the emitter base junction, and this is called the base collector junction, or the collector base junction, right? And for us to operate this device in active mode as an amplifier, we want to forward bias the emitter base junction and reverse bias the collector base junction. If we do that, then we found that electrons diffuse, and we made sure that the base is a very narrow region. So if we do that, electrons diffuse over to the base. They don't find opportunities to recombine with holes. So what happens is this is a reverse bias junction. The electric field pulls the electrons or collects the electrons in the collector, right? So the majority of the electrons move from the emitter all the way to the collector. Very few of them stay in the base. Some recombine, and then because this base is forward biased, so diffusion is due to electrons here to the base and holes from here to the emitter, right? So there is some base current due to this diffusion happening and this recombination happening here, but the majority of the electrons in the emitter are pushed all the way to the collector, right? Meaning the current is from the collector to the emitter, right? Since it's the opposite direction as the electrons. And we made sure that is the case by forward biasing this junction. So we put a voltage that is higher here versus on the emitter side, and we reverse bias this junction by placing a voltage here on the collector side that is higher than the base. But we said that, again, this VCB voltage, if I make it 0, I'm still not forward biasing the device. If I make it minus 0.1, I'm still not forward biasing. I have to overcome the barrier voltage to forward bias the device, right? So that can happen around, it depends on the concentration. If you go back to the semiconductors chapter, we will see that the barrier voltage depends on the concentration of donor atoms and acceptor atoms, right? So I can control that. I can control the barrier voltage. So it is controlled here to be around 0.4 for the collector base junction. 0.4, 0.5 is typical values for the forward voltage, versus the forward voltage for this emitter base junction is about 0.7, which is what we saw before, right? With the diodes, typical silicon diode. Okay? So that's summary of the operation of the device. And we want to operate it in this mode, forward here, reverse here, to operate as an amplifier. If we reverse both, then what's going to happen? If I reverse both, then there's no diffusion happening. If there's no diffusion happening, then there is no current electrons to be pushed over the other side when this is reverse biased as well. So there's no current going to flow, right? So if both are reversed. How about if both are forward biased? If both are forward biased, what's going to happen? The electrons here are going to diffuse actually to the base, right? So what's that going to do to the collector current? So remember here the collector current, emitter current was a certain width, right? Diffused the electrons to here, but they didn't find places to go, so they were pushed here by the electric field. Now, if I forward bias this, what's going to happen? I'm also going to push these through. These will diffuse. The electrons will diffuse. This is forward biased as well. This junction is forward biased. Electrons here will diffuse. Base current will also go. The holes will also diffuse into this and onto this side, right? So there will be a current from the base to the collector, right? There will be a current component there, and then there will be diffusion of these electrons to the base. So that's a component there. What will that do? It means it will reduce the amount of electrons creating the collector current. Since now they're not going to move this way, they're going to move into the base, right? So the amount of electrons carrying charges, causing current to flow, will decrease in the collector. Right, so we will see that if I put forward, then I go into what is called saturation mode. In saturation mode, what happens is the collector current decreases, and there is a component of current between the base and the collector A. So we will model that later in the chapter. And we said that at the edge of this saturation versus active region happening, right? At the edge between active region and saturation, what's happening? I have just basically forward biased this one, right? We said that saturation is when this is forward biased. The collector base junction is forward biased. When is this forward biased? We said that this is forward biased if the collector base voltage becomes more positive here versus negative. How much more positive? It has to be about 0.4 or 0.5 volts more positive, right? So what does that do to my collector emitter voltage that we discussed yesterday? We said that this voltage plus this voltage is equal to this voltage. This is collector emitter voltage, VCE, this is VBE, and this is VCB. These two added together are VCE, correct? Okay. When is this forward biased? When this VCB becomes negative. How much negative? 0.4, 0.5, right? If this is about 0.5 volts in this direction, and this is 0.7 volts in this direction, because this is forward biased. So this is 0.5 in this direction, this is 0.7 in this other direction, opposite direction, right? What does that do to VCE? VCE will be 0.2 volts in the same direction, right? Do we agree? So at the edge of saturation, beyond saturation. So at 0.4, this is where the edge of saturation. You know, if you're deep into saturation, you're not 0.4, you're about 0.5. Okay? So deep into saturation, this is the sort of the situation. This is forward biased, fully forward biased, but we said that we control the barrier voltage to make it 0.5 instead of 0.4. This is forward biased, 0.7 volts is the forward voltage, right? So deep into saturation, the VCE is about 0.2 volts. This is VCE saturation. We will see that. We will see this later in the chapter. So this is VCE saturation. So now we discussed the different modes. We're okay with how this device operates? Okay. So, and then we went through the equations for collector current. We said that collector current equation looks like the diode equation, right? What's the value of the saturation current? Saturation current, like in the diode, depends on the area, diffusivity, charge, width. I mean, it's a parameter that depends on the design of the device, right? And then we said that the base current and the collector current are related. The base current has several. We said it has two components. It's component due to the base holes diffusing into the emitter side, and then a component due to the electrons that have moved in here and have moved into the base region. But we said the base region is very small anyway, and this electric field is going to pull anything forward. So this is a small value, and this is a small value, right? But they contribute to what is called base current. And since it's small, and it depends on what happened in the device, what happened, meaning forward biasing here and reverse biasing here, this is really what controlled the amount of base current. Because I've forward biased this diode, that's why the holes have diffused here. That contributed to base current. Because I forward biased this diode, that contributed to the electrons that are moved into the base, right? So both of these components have the same exponential format, right? But they are scaled versions of the full value of current, right? But they have the same exponential format because they were due to diffusion, right? So they have the same format but scaled. Scaled with what? Scaled with a current gain called beta. And we will see that this is called the common emitter current gain. We will see why it's called the common emitter current gain. Okay, so that's the base current. Emitter current, obviously from the curve here, emitter current is gonna be very close to the collector current, right? So there will be also a constant that relates them, and it will be called alpha. And it will be the common base current gain. So it would be another constant that relates these two. Why are they related by a constant? Again, because the current is mainly due to the electrons being injected from the emitter to the base to the collector. And that was due to the diffusion process, which produces an exponential relationship between the voltage and current. Which voltage? The voltage that caused this whole diffusion to start, which was what? The VBE voltage, because we said I can remove VCB completely, put zero. And this junction will still be reverse biased. So what is really pushing this diffusion forward? It's the VBE voltage. And the fact that I made a very narrow base and I controlled the concentrations accordingly. Okay? So collector and emitter currents will be related by a constant. This constant will be very close to 1, obviously. The thickness, the amount of electrons here versus the amount of electrons here is very similar. So alpha will be very close to 1. Beta, I beta, this amount of current due to these charges here is much smaller than the amount of current due to the electrons that move forward, which means beta is a very large value. A few hundreds, maximum 1,000. So, which means the base current is smaller than the collector current. And then emitter current is the addition of the collector current and the base current. We did some manipulation of that yesterday, and we related the emitter current and the base current by this beta plus 1 over beta, and we called it alpha. Okay? Or, alpha is beta over beta plus 1. Okay, so we're okay with this now, the relationship between the currents. And we talked about values for alpha and values for beta. So alpha very close to 1, beta is large, between 200 to 1,000, for example. Why it's called the common base current gain, we will see right now. So we looked at these equivalent circuits as well, and we will show later the actual circuit diagram. And we will this idea of calling it a common base or a common emitter or a common collector configuration depends on which of the terminals is actually connected to ground directly. So in a common base configuration, the base will be connected to ground, the emitter and collector will be connected to other components. We will show that later in the chapter. But to start solving some problems, we have to, based on the physics that we discussed, we come up with equivalent circuits. Equivalent circuits should, comply with what we talked about before, right? We said that the collector current and the emitter current are very close. They're very close, which means that fine. And the emitter current is actually sum of the base current and the collector current. The base current coming here, collector current coming here, and they add up to this emitter current. And the collector current is this exponential function controlled by a voltage. So we've created a voltage-controlled current source, and this is a voltage control current source model. This is also a voltage control current source model, but it's a different configuration. It's called the common emitter configuration, but it's the same physics, right? I have base current coming in here. I'm forward biasing the base to emitter voltage, base to emitter junction. It's forward biased with IB flowing through it. This IB is added to IC to flow into the emitter, to flow out of the emitter. What is IC? IC is the same exponential that we have here. Okay? So these two we've created current sources that are voltage controlled. And here, instead of putting IC equal to a certain value, I put the relationship between, we know that IC is equal to alpha IE. So I just said, okay, instead of putting the exponential here and calling this a voltage controlled current source, I will put, the current source here. I will call this the current source gain. I'll call it alpha IE. Okay, so, and this now I've created a current source, and same for the common emitter configuration. The common emitter configuration, same, that I have the base current being added to the collector current. Collector current is equal to beta IB or alpha IE. It's either related to, we said that the collector over the base IC or IB is equal to IC over beta, or IC is equal to alpha IE. So these were equations that we came up with in the last section. So here I replaced IC with alpha IE, Here I replace the IC with beta IB. Okay? So, and you can use any of these models in an example, depending on what values or parameters you're given, right? So some examples will give you, the voltage, the base to emitter voltage. Some may give you the emitter current. Depending on what you are given, you remove the device and put the equivalent circuit that's corresponding to the information you are given. And by the way, all of this is only valid in the active region, right? Only in the active region am I forward biasing the base emitter voltage, and I'm creating a current source between the collector and the emitter. Only in the active region. I will show you another model for the edge of saturation and then deep saturation. I will give different models for those. So we're okay with that. But again, our concern in this course is mainly amplifier operation. So we're okay with the models? We'll do an example. So here, they give us, okay, so they have an NPN transistor with a saturation current is of so-and-so, beta is so-and-so, is connected as follows. So the emitter is grounded, and the base is fed with a constant current source, supplying a DC current of 10 microamps. So they're telling, okay, so the base has a DC current source supplying it of 10 microamps, and the emitter is grounded. And the collector is connected to a 5-volt DC supply via a resistance of 3 kilo ohms. So this is the collector connected to a 5-volt DC supply through a resistor of 3 kilo ohm. Assuming the transistor is operating the active mode, right? Which means I can remove the transistor and put my circuit, my equivalent circuit. Find VBE and VCE. Use these values to verify active mode operation. Replace the current source with a resistance. Yeah, let's do that first, and then we'll replace the current source with a resistance connected from the base to the 5-volt DC supply. What resistance is needed to get the same result? Okay, let's first do the first part. Yeah. So this is the equivalent circuit of the problem that we are discussing. They just told us that it's an active region, so I can replace it with this. I have a current source here and a resistor here, and they want to calculate VBE and VCE. So this current is moving into this diode. This diode is going to be forward biased, right? I have a current source pushing current forward into this device, and the device is in active region, which means the base emitter junction is forward biased. So what is the voltage across VBE? For forward biased silicon diode, the voltage is 0.7 volts, right? If it's forward biased, and we said that the base emitter voltage is doped the base emitter voltage is doped in a certain way, so that I create a forward voltage or a barrier voltage of about 0.7 volts across it. Yeah. So we know that it's approximately that, but let's see. We are supposed to use the operating conditions to solve that. Yeah. So I know it's going to be 0.7 volts. So the emitter is grounded, and the base is fed with a constant current source supplying a DC current of 10 microamps. So this is a diode, right? I'm pushing 10 microamps through it, and they want the voltage. So if with 10 microamp, I have a saturation current of a certain value through the diode, right? What does the diode voltage current relationship look like? Remember, V diode was, or I will remove V diode here and put VBE, okay? Because the voltage across the diode, this is my diode here now. This is my diode, right? This is the diode in the model between the base and the emitter voltage, right? The PN junction that I have. This is my P, this is my N. I forward bias this. This is a diode. So the diode voltage current relationships look like what? I had VBE, or I had V diode before in the last chapter, right? Versus what? I diode, right? Here it's going to be I base. Correct? The diode current is base current. The voltage across the diode is VBE. So instead of the V diode, I diode before, we will have to put VBE and I base. But what does the relationship between voltage across the diode and current through the diode look like? This exponential function. Correct? based on the diodes chapter. The current and the voltage across the diode look like this, and we know that this here
VDS
is what?
No, I was just talking about the saturation and the triode region. Sorry.
No, we're not. We're just looking at the current through this junction. Okay, so this is a typical diode characteristic, and we know that the voltage here is around 0.7, around 0.7 volts. This is where the diode current becomes very high, and the voltage doesn't change too much. Around when does that happen? Around 0.7. But now they want the exact value of the voltage across the device. So here, the emitter is grounded. Assuming the transistors are operating in active mode, find VBE and find VCE. So how do you find VBE? VBE is basically the voltage across the diode. So if the diode is not conducting, the voltage across it is 0. If the diode is conducting 10 microamps, what is the voltage across it? Right? Remember, we came up with one equation. The equation for current for the diode was what? I diode was equal to IS e to the voltage across the diode, which in this case VBE, correct? Over VT. That was the equation for diode current, correct? So I will replace this with base current, right? We said this is diode current is base current. And I will call this, 1. And I will call, and then IS is the same for at any point. This is for the same diode. IS is the same. The saturation current is the same because it depends on the diode dimensions, the charge, the area, doping, etc., etc. And then I will have I base 2 is equal to I saturation E to the VBE 2. This is VBE 1. This is the voltage across the diode 1. Current through the diode 1. Then voltage across the diode 2, and then current through the diode 2. VT is the same, obviously. At room temperature is 25 millivolts. And then in the diodes chapter, we did what? We did the ratio between them. So we did IB2 over IB1 is equal to, the IS's go away. They cancel with each other. And I'm left with E to the VB2 VBE 2 minus VBE 1, correct? Over VT. I took the natural log of both sides. If I take the natural log of both sides, white background. If I take the natural log of both sides, then I have natural log of IB 2 over IB 1 is equal to the difference in voltage. Remember, what operating points am I looking at here? I'm looking at the case where I am saturated, right? There's no, I'm blocked. When the current is, when the diode is not forward biased, it is reverse biased, and it will have a certain value for saturation current, right? And that's going to happen where here, I'm reverse biased. At some condition, I'm reverse biased, right? And then the other point is what? And the voltage across this case is 0, right? How about this at this point here, 10 microamps, right? At 10 microamp, I have a certain voltage across the diode. This is now what? This is now VBE that I'm looking for. It's the difference between these two voltages. The difference between these two voltages, right? So if I take the natural log on both sides, then I have VBE here over VT. I can bring VT to this side, and I have this equation, right? So, and that's what they used in the example. So everybody's okay with this? So this is one operating condition, another operating condition, the difference between the voltage across the diode between these two operating conditions. Okay? So it's the same equation we used in the diodes chapter, but they just threw it out there in the example here right away. Okay, so this is the 10 microamp, the 10 microamp case, and this is what? Base current when the device is saturated. When the device is saturated, the collector current is equal to IS e to the VBE over VT. What is the base current equal to? IC is equal to IS e to the VBE over VT. What is I base? Compared to IC, I base is equal to IC over beta. Right? That's why the second operating, remember we had two currents, one operating condition here. This is the 10 microamps that I had flowing through my device. 10 microamps. The other one was the saturation. Device is off. Right? Saturation, the junction was reverse biased. What's happening there? And there I have saturation current flowing through. What value of saturation current? The saturation current for the collector is IS. Saturation current for the base is proportional to IS over beta, because it's IC over beta. So that's why they put IS over beta here. We're okay with that? That's my second operating condition. And then you just substitute. So this was 25 millivolts, and this is the 10 microamps, and this is IS over beta. They gave us IS in the problem. IS was 10 to the minus 15 amps, and beta was 100. So IS over beta is 10 to the minus 17. Right? So this is IS over beta, 10 to the minus 17. So we calculated VBE to be 0.69 volts. Is it far away from 0.7? No, it's not far away from 0.7. So typically, when we're starting to, when we're designing circuits, we will typically utilize, 0.7. Then what? Okay, so now that if I have my VBE voltage, if I have this, my VBE voltage, that is something I have now, and I know my base current, I know beta. What does that mean? That means I know IC, right? I'm giving beta as 100. I'm giving IB to be 10 microamps. So I know beta times IB. So this current is flowing through this resistor. They're trying to calculate VCE. What is VCE equal to? VCE is equal to 5 volts, which is where this resistor is connected, minus that current times the voltage drop across the resistor. Right? Minus the current times the resistance, which is the voltage drop across this resistor. So, and that's what we have here. VCE is equal to VCC, it's the 5 volts, minus RC times IC. IC was the beta times IB that we calculated, hence VCE is 2 volts. Okay? So, if VCE is 2 volts, VCE is the addition of what? VCE was here, remember VCE, and this was VBE, and this was VCB. This is my emitter, base, collector, right? VCE now is 2 volts, right? What was my saturation point? What was my saturation value for VCE? VCE sat was equal to what? About 0.2, right? So I'm nowhere close to that, right? I'm much higher than that, right? Since I'm much higher than that, again, VCE is the addition of these two. We calculate this as 0.69 volts, and which means this is what? About 1.3 volts, right? So if these two are positive, then what did I do? This is my device. Right? This is my emitter, base, collector. This is here, and this is here. This is NPN. So this is positive and equal to greater than 0.69, which means this junction is what? Forward biased or reverse biased? Forward biased. Right? How about this? This is 1.3 volts. Which means this junction is forward biased or reverse biased? Forward biased as well. No, 1.3 volt. This junction is forward biased or reverse biased? This is N here, sorry. This is N. So I have a higher voltage on the N side than the P side. So this is forward bias or reverse bias? Reverse bias, right? So this is forward bias, this is reverse bias, which confirms that I'm in the active region, right? So even if this was 0, right? Even if this was 0, I'm still in the active region. When this becomes minus 0.4, then I'm at the edge of saturation. Okay? So does everybody see what we did here? Okay? Fine. And after that, what did I do? So after calculating VCE, after you calculate VCE here, so I think we're done with this, with what they asked for here. So, and then the next thing they asked for is what? So we calculate VBE and VCE. We confirm that we're in the active mode. Use these values to verify active mode operation. We did that. Replace the current source with the resistance connected from the base to the 5-volt DC supply. So I connected this resistor here between the base and 5-volt DC supply. What resistance value is needed to result in the same operating conditions? So basically, what am I asking for here again? So if this is connected to ground, and we calculated this to be what? The base to emitter voltage, we calculated this to be about 0.69, right? So this is connected to ground. This is 0.69 volts that I have here. So they're asking us, okay, what is the value of resistance that I have to put here? This resistance is equal to what? This resistance, we're connecting this to 5 volts. So it's 5 volts here. What is the voltage at the base? With respect to the emitter, it's 0.69. So I know the voltage on this side of the resistor, 5 volts. And the voltage on the other side of the resistor is 0.69 volts. Subtract and divide it by this value of resistance. I should get the current through the diode, right? But what is the current through the diode that we want to operate at? So do I have the they maintain the same operating conditions. So they want the same 10 microamps that they give us before. So the same operating condition that they initially described. The diode has 10 microamps. So we're going to assume that diode has 10 microamps flowing through it. And given that I know the value of base current, I know the value of voltage here. The difference between the voltages divided by the resistance is 10 microamps. So you can solve for the resistance R base. That's what they did here. 5 minus 0.69 divided by 10 microamps is the R base. Okay? So all of this is tricking you into the same thing that we described with the MOSFET, right? All of this is the DC operating condition, right? So what we did in the MOSFET is the same exact. So this is like a review for the MOSFET chapter, except different terminology. So here we start with the device, physics, then large signal model, and then we started calculating steady state DC values of the voltages at the terminals. In the MOSFET, we were calculating the source voltage, gate voltage, and drain voltage. These defined my voltages of the voltage terminals of the device, and the different levels between them defined if the device was operating in amplifier mode, or in the MOSFET, it's called saturation mode, right? Or it was operating in triode mode, or it was operating in cutoff. Here it's the same thing. We will find that these voltages, the voltages at the base, collector and emitter, will define if the device is operating in amplifier mode, which is called active region in this case, or saturation, which is like the triode region in the MOSFET, or cutoff. Okay, so it's exact same, just the terminology is different and the physics of the device is different. There we had a gate to source voltage. Here we have a base to emitter voltage that is causing current to flow all the time, right? The structure of the device is very different than the MOSFET. So again, we said it's 2 p-n junction. What we showed before was a simple, P area, P material between two N-side materials. How do you really construct this? The way they really construct this is, you get an N substrate, and then you add some P material onto it, and then you add some N material onto it, and then you have your NPN transistor this way. So unlike the MOSFET, it's not symmetric, right? In the MOSFET, we had a very symmetric device. I can swap the gate, I can swap the drain and the source. I will have no problem, no changes. Here I cannot swap the emitter and the collector. Obviously, we said before that we are doping them differently so that we can control the barrier voltage. Remember? I mean, we said that we want the barrier voltage to be different between the base emitter junction and the base collector junction. You know, this the 0.4 versus 0.7 that we discussed. So that requires the device to be not symmetric. It will not be a symmetric device. Right? So this is how they construct it. Just something for you to look at and understand that they are not. It's not reversible. It's not symmetric. Yeah. Okay. So now saturation mode. In saturation mode, we said we will have. If this is my device, I will draw my device up here. This is NPN. We said that in saturation, I will what? I will forward bias this junction, and I will forward bias this junction, but I will draw the voltage this way, but I will write here negative. Right? If I'm going to forward bias this junction, I have voltage at the P is higher than the N. Right? So, but if I draw the positive this side, I will have to make this voltage value negative. Negative, let's say 0.4, for example, is when I will be able to overcome the barrier voltage of this junction and make it a forward bias device. And then here I will put some positive value of voltage, whatever, 1 volt. Or I can say 0.7 or 1 volt, whatever. So I forward bias this junction, right? So this is a voltage here is more positive than here. So this junction here, the emitter base junction is forward biased, and the collector base junction is forward biased. If both are forward biased, then what did I do versus before? Before we said that the electrons were moving from the emitter to the base. They have nowhere to go in the base because it's very thin base, and they find that this junction is reverse biased, so there's an electric field here pushing them through to the collector. So the electrons are basically moving from the emitter all the way to the collector. That's what was happening before. Now, in this case, that's not the same case anymore. Now, this is forward biased, this junction is forward biased, and this junction are forward biased. So I have diffusion from the emitter to the base, and I have of electrons, and I have diffusion of electrons from the collector to the base as well, right? This means that the electrons have moved from here to the base, but then they're not easily moving forward because now this is a forward biased junction. When the diode is forward biased, what happens? The charges diffuse, right? The mechanism of charge of the current conduction is diffusion, not drift. Before this was reverse biased, I was forcing the electrons that moved from the emitter to the base to drift over to the collector. Now I'm forward biasing this junction as well, so I'm causing diffusion of the electrons from the collector to the base, which means I've decreased collector current. Right? It means I've decreased collector current. And I've also increased base current. So base current was here. Only base current was due to what before? Electrons were moving from the emitter to the base. Some were staying here, and some, because this was a forward bias junction, some of the holes were moving from the base to the emitter. So there was some diffusion current there as well. And that was causing the base current here. Now, I'm also forward biasing this. So there's more holes diffusing from the base to the collector as well, which means that the base current increases. So base current, not I beta, so base current increases. And the collector current is decreasing in saturation mode. Right? Do you see what happened with in saturation when I forward biased both? So if this is the case, then we need to put some equations to that. And when is this happening? We said that this is happening when this voltage here is about 0.4 volts or minus 0.4 volts if I draw the power supply this way, because that's when this the collector-base junction becomes forward biased. So, that being the case, let's put some equations. We said that the collector current is decreasing. Decreasing by how much? Right? Decreasing by current caused by what? Current caused by this voltage. This voltage is what? VCB. When VCB became negative, or VBC became positive, right? When VCB became negative or VBC became positive by more than 0.4 volts, this junction, the collector base junction, started to conduct. How does it conduct? It conducts by diffusion. Conducts by diffusion means it follows the exponential equation. IS equal to IS, the current is equal to IS times E to the voltage that produced that diffusion divided by VT. What voltage produced that diffusion? It's VBC. Right? It's the voltage between the base and the collector produced that diffusion that decreased the current that was originally flowing through the device due to the diffusion across the first junction, the VBE junction. Okay? Yes? You see where why this is VBE and this is VBC? Okay? So, and of course the opposite is happening to the base. We said that the base current is now going to increase. Increase due to what? Due to the same voltage that caused the decrease in the collector current. So it's the same amount of current that was decreased. The electrons had to go somewhere. Where did they go? They went from the collector to the base. So now they increase the base current by the same amount due to the same voltage. Okay, so this is the decrease in the collector current, increase in the base current. But I have to put these in a circuit now. Find an equivalent circuit to put these in. But before I do that, so that we just graphically represent what we have here. So this curve says what? This graph says that in the active region, my device is a nice amplifier. I have current that is independent of the voltage across the junction. Really nice. It's dependent on the voltage across another junction. So, which means I can control the voltage across another junction to produce a current source at the output. That is the beauty of the amplifier mode of operation, right? But if I get into saturation, what's happening at saturation? At saturation, this voltage across the base collector junction is now going to be reverse biased, or the VCB or VCB becomes negative, or VBC becomes positive. Here because they're very confusing. Here they write VBC. VBC becomes positive. That's the 0.4 volts. Or the VCB becomes negative. That's the way I drew it was to explain this minus 0.4 volts. Okay, so if I make VCB more about minus 0.4 volts, that's the sort of the edge of the active region of operation. So until this point, the junction was reverse biased. The collector base junction was reverse biased, and I have the amplifier mode of operation. At this point, minus 0.4 volts for VCB, I'm going into saturation. Deep into saturation, we said what? We said deep into saturation, the VCE becomes 0.2 volts. VCB becomes, about 0.5. This becomes like a reverse bias diode. You remember what happens with diodes? As soon as they're forward biased, the voltage doesn't change much and current changes a lot. Right? So this is what happened here. The current changed a lot, decreased considerably, and the voltage didn't change much. Here it's about 0.5 volts. We're okay with this? So now whatever we describe now, we'll put into a circuit. So the circuit will still have to have my main terminals, my base, the collector, and the emitter. What was happening to the base current? The base current is increasing. So the base current before was this diode current that I had here, forward biased diode current controlled by the base emitter voltage. Now the new base current is this same old diode current plus the current that decreased from the collector. Right? So it's the base current. The base current is the same old diode current that I had, which is the old IC over B, over beta, right? Plus the current that decreased from the collector, right? So that's why I've added this diode here, and this diode current is what decreased from the collector. So obviously this is decreasing collector current, and it's increasing base current. So this is the new equivalent circuit for the device. At the edge of this circuit is not valid anywhere. This circuit is only valid at the edge of the saturation active mode region. Only at the edge. After that, it doesn't become valid anymore. When deep into saturation, remember, the current is changing a lot, significantly. It's dropping down to, the collector current is dropping down to 0. If the collector current drops down to 0, I can remove this. Right? And then when it drops down to 0, the voltage is not changing as well either. The collector current drops down to 0, and the collector emitter voltage becomes a fixed value of voltage due to this, due to the fact that the collector current dropped down to 0, and now my collector base voltage is a fixed value, 0.5. So my collector base voltage is a fixed value, 0.5. So again, my device, my collector base voltage became a fixed value, 0.5, but with a negative sign, right? Negative 0.5, right? So this is negative 0.5, and this is 0.7 because this is forward bias still, means that my VCE voltage will become the saturation voltage deep in saturation equal to 0.2 volts, right? So this becoming 0.5, the VCB becoming minus 0.5 corresponds to a VCE saturation voltage of 0.2. We will see why that becomes important, because this is in my model. I have the terminals between the collector and emitter. What do I remove? Okay, I remove this because now I have 0 current between them, right? The current dropped to 0. The collector current dropped to 0. The collector current dropped to 0 because this current has overcome that completely. So the collector current drops down to 0. Okay, so how do I model all of this? And then it drops down to 0, but then my VCE voltage, which is the voltage between the collector and emitter, became a fixed value, 0.2. So I have to remove this and this diode and this current source, and model this new physics using something else. What is a good way to model this new physics? At the input, this is forward bias, deep in saturation. Deep in saturation means now both junctions are forward biased. If the diode is forward biased, what does it look like? A voltage source opposing current flow. This here I will remove. And I know that my junction now is forward biased. My collector emitter junction, I will model my VCE voltage. Remember, my VCE SAT was 0.2 volts. We know that. We know because of the fact that my collector base voltage became minus 0.5, fixed value, the current decreased down to 0 and the voltage became minus 0.5. My base emitter voltage is 0.7 because the base emitter diode is forward biased. What does this mean? It means my collector emitter voltage will become 0.2. So I will remove these two, and I will just model this as, okay, and at the input I have a voltage source, and at the output I have a voltage source. This has a value of 0.2. This is emitter, this is collector, this is base. This has a value of 0.7. Does it make sense? So we have now an equivalent circuit in the active region, or set of equivalent circuit in the active region, because that's the most important region for us to play with. We want to design different amplifier circuits, and these different amplifier circuits will require different characteristics. We will discuss that later in the chapter. So we have 4 different equivalent circuit models there that we've introduced. Then we introduced an equivalent circuit for operating at the edge of saturation. Then we introduced an equivalent circuit that's very simple to operate at deep into saturation. Deep into saturation is where the switch mode of operation. Right? Switch mode is when the device is on, I have 0.2 volts across it. Device is off, it's an open circuit, right? So it's cut off meaning. Okay, so since the collector current decreases considerably, remember what was beta? Beta, the current gain, beta was related what? Related the base current with the collector current, right? And this was in amplifier mode, this was a fixed value because it was my base current that was controlling my output collector current, right? So they were linked with a gain of beta, and it was pretty much a fixed value for the device, right? But now, if I look at what's happening here, in the deeper I go into saturation, the collector current decreases and the base current keeps increasing. Collector current decreases, base current keeps decreasing. Does this mean that the ratio beta is going to be fixed? Beta was, IB was equal to IC over beta. And beta, they were giving it, okay, 100 or 200 or 300. And that's it, right? It was a fixed value, right? Which means that if I increase IC, what happens to IB? Come on. If beta is a fixed constant value, if I increase IC, what happens to IB?
It increases.
Increases as well, right? This is nice, and this is applicable in active region. Now, if I'm pushing into saturation, and when I push myself into saturation, anytime I go deeper into saturation, what's happening? IC is decreasing, while IB is increasing, right? This is decreasing, this is increasing. I'm adding here, I'm subtracting here. What does this mean for beta? Is beta fixed anymore? And beta was relating these two together with a fixed quantity, right? Now beta will still relate these two. Beta will still be IC over IB. This is still the gain, but it will take on a different value every time you change your base collector voltage. The deeper you go into saturation, it will take a different value. And that's why they call it beta forced, meaning forced into saturation, right? So that's what they're referring to here, right? So, and beta forced, again, remember what was happening is collector current was decreasing, IC was decreasing, and IB was increasing. Before, again, beta was equal to IC over IB. It was a constant value. What happens now if I decrease IC and increase IB? What happens to the value of beta? Does it go up or down?
Say that again.
If I decrease IC and I increase IB, the base current, if I do that, what happens to beta? Does it go up or down?
Down.
Exactly, it goes down, right? So beta forced, which is an indication of you being in the saturation region, is going to be less than or equal to your device beta, right? So it's a number that will change. And this number will definitely be lower than your actual original device beta in the active region, because of the fact that the beta in the active region relates the IC and IB this way. Okay? So your check for being in the saturation mode is what? Is IC over IB, which is beta, or beta forced in this case, is less than your original beta. You were given beta of 100. Now you calculate beta, which is still IC over IB, but you calculate it to be 50. So you know you're in saturation mode. Right? The other check is the collector base junction is forward biased with more than 0.4 volts. Right? Or VCB is minus 0.5. Not, the limit is minus 0.4. So if it's forward biased, if the junction is forward biased by more than 0.4 volts, then you have pushed yourself into saturation, and the current will drop very quickly in saturation mode. Okay, so do we see? Can we? This is the check, and of course the corresponding. After this is what's happening right after getting into saturation. Deep into saturation, we came up with another model, right? The other model for the device, which is the VCE saturation model for the device. which we called, which we made 0.2 volts, and they draw that, I think, in the next, somewhere next upcoming section. Okay, so all of this discussion was about the NPN transistor. The PNP transistor we will not spend too much time on. Again, it's the same construction, right? It's the same two junctions. I have a base emitter junction and then a base collector junction. I still have to operate this in forward bias and this in reverse bias to get the same characteristic. Which means what? Which means that now I have to flip the voltage VBE. Remember, they used to call it VBE. Now they call it VEB. So they both remain positive. Okay. Because remember, for the MOSFET, we said we'll just use absolute values and stuff like that for the MOSFET discussion. Here, instead of using absolute values, fine, they flip the source polarity, or instead of VBE, they will write VEB, right? Which means that they flip the polarity, right? But so basically, I flip the polarity of everything. But the discussion is exactly the same. The main difference is before, the current conduction was due to electrons diffusing from the emitter to the collector. Now it's due to holes diffusing from the emitter to the collector. But the process is exactly the same. The physics is exactly complementary, basically. Okay? Yes? No? What else changes? Since it's holes that are moving from the emitter to the collector, the direction of current changes. So before, current was flowing from the collector to the emitter because it was due to electrons moving from the emitter to the collector. Now I have holes moving from emitter to the collector, which means the current is in the same direction as the holes moving from the emitter to the collector. Right? So I've reversed the same as the MOSFET. MOSFET also will reverse the current. Right? And that's why when we drew the circuit model, we drew the source on top for the PMOS versus the drain on top for the NMOS. Here it's exactly the same. Exactly the same. Right? That's why I'm saying this chapter can be like a review to what you're doing in the MOSFET, with what you're studying in the MOSFET chapter, but with different terminology, different values, so it makes you even more confused. Right? So any questions really on this? Is it overwhelming?
I know.
Maybe when we solve it, a few examples should be. The model is the same. The model is the same. So we've created a current source, and this current source is controlled by the emitter to base voltage, and this is a diode current, so it follows the same diode current equation. I'm still having to forward bias my emitter base junction, so the emitter base voltage is modeled, is a voltage, and the junction is modeled as a diode. So you're still modeling this as a diode so that you know that it's diode current equation that is applied here. And the emitter and collector currents are still related by alpha. Same, the equation for the relationship between IC is equal to alpha IE. Same as the NPN transistor. So the model is exactly the same. So this is the common, exactly the same, except I've changed instead of VBE, I've used VEB. Here, so I flipped all the voltage polarities, and I'm showing the direction of current. I'm putting the emitter on top because the way that this textbook likes to do it is, current flows from top to bottom. So we flip the emitter and collector terminals, the same way we did for the MOSFET. Yeah. So this is the common base configuration or model, and this is the common emitter configuration or model. Okay? And you can use either. When do you use this? When do you use that? Okay. Again, we said that when we say common base, it will refer to circuits where the base of the device is connected to ground. The other two terminals are connected to different things in the circuit. A common emitter configuration means the emitter is connected to the ground, and the other two terminals are connected to the rest of the circuit. Okay, that's what this refers to. Okay. Like we did for the MOSFET, of course, now we have to introduce a circuit model. And then after we do the circuit model, we do what? The voltage transfer characteristic. Same. We're following the same process exactly. Right? So the circuit model for the device is also very similar to the MOSFET model. So here for the NPN, so this is the NPN transistor. The arrow here is always, so this is N, P, N. The arrow is always on the emitter. The arrow is always at the emitter. Okay, so the arrow is always at the emitter, between the emitter and base. The emitter and base. So the arrow is always between the emitter and base, and the arrow is always pointing towards the N. So this is P, N, P, right? The arrow is always pointing towards the N. Okay, so and it's pointing towards the direction of current flow as well, right? We want current to flow this way. Right, so that's the circuit model that people came up with, and this is the the DC bias point operating model. We have to remember that for us to operate this in active mode, the base to emitter voltage has to be positive, right? It has to be positive, and meaning it has to forward bias this PN junction. Meaning it has to be positive and greater than 0.7. So I should have said that as well, right? Because if it's forward biased, then the junction will respond by a voltage that opposes the current of 0.7, approximately. So this has to be positive and greater than 0.7. Same thing with this. Because I still have to forward bias this junction. This is my PNP transistor. I still have to forward bias this. So this VEB now has to be positive and greater than 0.7 as well. How about the VCB voltage and the VBC voltage? I have to reverse bias this. This is an N. This is an N. This is a P. So I have to reverse bias this junction. For me to reverse bias this junction, I have to put a voltage on the N side that is higher than the P side. But because this is a diode that has a barrier voltage, I also have to overcome the barrier voltage. Right, so VCB can be 0, and this junction here, this PN junction, the collector base junction, is not reverse biased. This VCB can be all the way up to minus 0.4 volts. At minus 0.4, beyond minus 0.4 volts, i.e. minus 0.5, for example, then I forward bias the collector base junction, and I'm not operating in active region anymore. And the same thing with here. I'm reverse biasing the base collector junction by making the voltage on the base higher than the collector, because this is an N on the base side, P on the collector side. If I make VBC negative, I flip it, I will forward bias the junction. When does this happen? At VBC about negative 0.4 volts as well. Okay? Same, they're just exactly complementary. So from a circuit design perspective, it will be very easy to look at what's happening here. So they summarized the equations that we talked about, all the equations that we discussed for the device here, and they tell you for the PNP transistor, just replace VBE with VEB. Really, that's all they're doing, which means that I'm replacing all the voltages with negative values, right? And it makes sense, because we now have a PNP instead of an NPN transistor. I will skip this section about collector base reverse current. It's not very important. And then I wanted to do this example. I'll do this example quickly, okay? So here it's a very quick, short example. Basically, like what we did with the model, but now fine. I know that the model exists, but do I really have to put it in every time, or is there an easier way to do it? So here they tell you that the transistor in the circuit of figure 6.41 has a beta of 100 and exhibits a VBE of 0.7 volts. So beta equals 100 and VBE equals 0.7 volts at IC equals 1 milliamp. So design a circuit so that the current of 2 milliamps flows through the collector. So they want a current of 2 milliamps. So they're telling us that they want IC to be 2 milliamps to the collector, and the voltage of 5 volts appears at the collector, and the voltage of 5 volts. So they're giving us this, and they're giving us 5 volts, and they're asking us basically to find the value for RC and the value for RE. That's basically what they're asking for. Okay, so how do you find the so they're giving you 5 volts. They're telling you that this is 15 volts. They're telling you that this is 2 milliamps. So you can calculate RC, right? So you have RC now, and we know that IB and IC are related by beta. So IB with the base current is equal to IC is over beta. So I can calculate the base current as well, right? If I know my base current and I know my collector current, what is the emitter current equal to? Collector current plus base current, right? So collector current plus base current is equal to the emitter current. So I can calculate my emitter current. I know my emitter current and I know the voltage here. But I don't know the voltage here yet. Theoretically speaking, you don't. But do you really know it or not? The voltage at the base is 0, since this is grounded. And that they're telling you that at 1 milliamp collector current, the base emitter voltage is 0.7. So now my collector current is 2 milliamps, right? Which means that the base current will change, which means that this voltage is not 0.7, it's something close to 0.7. How do I find this voltage? Again, it's a forward biased junction, right? If it's a forward biased junction, I have to do the diode characteristic. Remember that VT equation? The VBE equation is equal to VT times natural log I over I, right? That we did at the beginning of the class. So you will have to find, so one condition is 1 milliamp. The other condition is 2 milliamp. At 1 milliamp, I have VBE equals 0.7. What is VBE at 2 milliamps? That's what they're trying to find. So, again, we can look at how they did it, but that's basically what they did. So it's it's the difference between if you go through the logic, you'll find that it's 0.717, very close to 0.7, right? So it's that was if you assumed it's 0.7. If you assumed it's 0.7, fine. What is it? Then this is 0. This is 0.7 volt. Then the VE is minus 0.7. Minus 0.7. This is minus 15 volts. So you know this is minus 15. This is minus 0.7. So and you know the current, which means you can find the resistor here, RE. Okay. So I've designed RE and IC and RC to do what? To create a certain collector voltage and a certain emitter voltage. So my emitter, this is forward biased, and now my collector voltage is 5 volts and my base voltage is 0. What does that mean about the collector base junction? If the collector voltage is 5 and the base voltage is 0, what is my collector base junction, forward or reversed?
Forward.
Why?
No, reverse.
It's reversed because this is my collector base voltage. This is my collector base voltage. My collector base voltage, this is 0 volts. This is 5 volts, right? Which means I've created this type of source connected across it, and this is NP here, N. So I've created a more positive N than a P, which means that the junction, the collector base junction, is reverse biased. So this is reverse biased and this is forward biased. So I'm operating in active mode. So we'll stop here and we'll continue with this DC characteristics tomorrow.